everybody, from your favorite artist electronist here, Mr. Q12. What I'm having here is the same test that I did before, but at very low values. Not as high as I was performing them the last time. The goal of this experiment here is to find out what happened to those MOSFETs that I managed to burn them so gloriously. Here they are, the 5 dead musketeers. I don't like to burn transistors, but that's life. So, like I said, this setup that I'm having here is at a very low settings than the one that I did previously. And I'm having 5 volts. And when I'm switching this switch, it is switching to 0.2 amps. That means 200 milliamps. Here on the oscilloscope, we can see those 0.2 amps, but as voltage, as this millivolts that you are seeing here, 222, yeah, 200, you see 202. And on the horizontal line, I'm having 100 milliseconds per each division. Here is the circuit diagram that I'm using with this circuit that you are seeing it here. So as you can see, the oscilloscope probes are over this one ohm resistor. I'm getting 5 volts or 0.2 amps from my variable power supply, that one. I'm providing 12 volts through this switch directly to the gate with this power supply, and both negative rails from my power supply 1 and power supply 2, all the both negative rails are common. You can see this blue wire is common with that wire as well. And over the MOSFET, I'm having this voltmeter telling me what is happening on the drain and source. It's like hinting me, is telling me if the MOSFET is dead or not. I'm keeping it in case I'm having a problem, but really it is not necessary to have the MOSFET in this particular case because all the values are very low. So right now, as it is conducting, it is passing through this resistor, specific this 1 ohm resistor that I'm having at 5 watts, that one there. I'm getting, on the oscilloscope, I'm getting that 200 millivolts that are translated into amps. So it's the same as my power supply there. In the moment I'm switching to off the gate of the MOSFET, you will see here on the oscilloscope, a drop to 0 volts, and everything got to 0 volts there. Also this, that's a voltage, but actually it's amperage because it's across that resistor. So is in accordance, the amperage there is in accordance with the reading on my oscilloscope. And now from off state that it is right now, when I'm closing the switch, it will activate the gate of the MOSFET, and you will see what is happening here on the oscillogram. So there. And let me actually freeze, redo the experiment and freeze it. You see, it got to 200, you see, 200 millivolts there, which it means 0.2 amps. But you see, after it passed, the pulse disappeared because this oscilloscope is refreshing the entire display when the line is reaching this point and starting from that point again. So yeah, I cannot read here that spike. It is a way, but I don't know it right now. How to perform it, how to catch the spike. But I can do it manually, and let me do it. Okay, so I catch and freeze. I stop from that button. I stop the waveform and I catch it here. So it's starting from 0 volts from here, is making this pulse or spike 1, 2, 3, 4 and a bit, and then is going down to 200 that you've seen earlier there, 200 millivolts, but it is corresponding to the amps there. So what I'm having here, I'm having 4 amps pulse. And why I'm calling it a pulse and not a spike, they are kind of interchangeably in this situation, but I'm calling it more as a pulse than a spike because the duration is very large. You see, if I'm having 100 milliseconds here, is 50 milliseconds there, the width of the pulse until it is getting low. And that's 50 milliseconds, it's quite a lot of time to pass for a spike. So that's why I'm calling it a pulse and not a spike. And that pulse is actually, power supply is switching from the voltage to the amperage, from the 5 volts to the 0.2 amps. And probably is catching a little bit of that voltage and is converting it into amperage. I don't know how it's created inside. It's having something inside that is unknown to me. But it appears like it's doing that. Basically what I'm doing here in my circuit, I'm shorting my power supply through the MOSFET. So basically the MOSFET must suffer this, must support, must endure this short circuit that I'm creating with my power supply. Right now my power supply, it is in short circuit. If I'm taking it from the circuit here, this alligator clips, and I'm shorting them together, they will be also 0.2 amps. Let me actually prove it, right? So I'm taking them out from here. Okay. And let's see what is happening when I'm shorting them. 0.2 amps, because I actually limited my power supply to 5 volts and to this 0.2 amps from this knob. This is the line of amperage and that is the line for the voltage. So I limited both of them. Let me connect it back as it was, and voila, it's back as it was. So you see, that's what is happening here. This MOSFET is resisting. I'm not sure how resistance is doing there, but at least is passing through it all this short circuit, and if the MOSFET is having a little bit of resistance inside it, that resistance will heat up the transistor when a lot of amperage is passing through it, basically. And it's doing this job perfectly, but with this spike in amperage that you are seeing there. And that is, we can calculate that. If we are having 4 amps divided by 0.2 equal 20 times. So this spike is 20 times larger than the average 0.2 amps that is constantly working or supporting this MOSFET to pass through it. So that's a very important spike and very dangerous spike. And that's why all my MOSFETs were blowing up. You see 5 volts, and that is 4 point something volts. So that pulse is trying to reach this 5 volts that I'm having here. So in my previous experiment, I was having it set to 10 volts there, and the pulse, I imagine, right now I'm deducting, it wanted to reach that 10 volts, so it got to 9 volts or something like that, I'm imagining. So let's calculate that. And and it was having 5 amps because I was turning down the knob, the amperage knob, to the maximum, so I was having that 5 amps there. So that 9 amps, presumably, divided by 5 amps equal 1.8 times greater than the average, the normal, the constant 5 amps that I was letting pass through the MOSFET. This is not much here on the paper, it's almost 2 times here on the calculator, but in reality that must have destroyed the poor MOSFET inside it. That must have burned it. Or the spike was even greater, like 20, like this 20 times that I'm reading it here, or even greater than that. But remember, I was doing this switching very, very fast. If I'm doing it rarely, it can support this pulsing that is from the power supply itself. But if I'm doing it faster, is not good for the MOSFET. Well, the MOSFET is burning. So this is all that I wanted to say about this experiment. It's a very interesting way of visualizing what is happening, especially that pulse or spike, whatever you want to call it. And with this experiment, I learned, I understood a bit more clearly that my MOSFET needs a load that is not too low. If the load is too low, that kind of spiking will occur over the MOSFET itself and destroy it. And like my friend said, and I did hear him, but with half an ear, my friend said that the MOSFET is there to switch the current into the load and to let the load to receive, to take all the power over it. The load should get hot and get all the power dissipation over it, and not the MOSFET itself. And now I'm starting to see the truth and wisdom in his argument. This experiment that I'm doing here, I'm actually testing to the worst case possible that a MOSFET can conduct and can work at. That's why I burned those fuckers before, because they were put to the worst possible way of working. And this, what I'm having right now, is not the worst, but it's still bad. It shouldn't switch on a shorted power rail, like I was having it like this, you see? This is still not good, but this is still the worst case scenario. Even if it's limited, problem is that I'm connecting it directly and with not a very big load. You should add a bigger load that will resist to the total power delivered from your power supply, or the power supply to adapt it to the load power that it needs. And the MOSFET will do its job to conduct all that current and deliver all the power for the load itself. But we should avoid letting all the power getting over the MOSFET, because it will burn it out. My problem that I'm having with this experiment that I started, and this extreme that I'm conducting the experiment, the MOSFET is driving all this power through it, all this current through it in this extreme situation. I started all of this to understand what is the maximum power that he can work with, that he can deliver and not get destroyed. And so far, I still didn't get to that answer. I'm still not happy with what I get so far, but I get something. I get some interesting experience and interesting knowledge about it. It bottoms to a MOSFET must work in conjunction with a load. That's it. This is the rule. Load and MOSFET, and that's it. If it's the case, the load is burning up. After the load is destroyed, then all the power gets over the MOSFET, and then the MOSFET gets destroyed. So this is how you destroy a MOSFET, by having a bad load at its inputs. So when you see on repair boards, on other boards, some burned out MOSFETs, this means that the load they were driving, that load is either dead or is damaged and is trying to get more power over it because of the damage, and is supra soliciting the MOSFET, and some percentage of the power is falling over the MOSFET, and thus is burning the fucker. So that's a little bit of theory and insight, but we should see all of this in practice, and I'm thinking on it right now. I'm not sure if I can find something good enough, but I want to see and to be able to predict its maximum power load that he can work with. So it depends on how powerful the load you put it on the input of the MOSFET. Pretty much this is what it boils down to when you are working with MOSFETs. Is extremely dependent on the load that you are adding to it. By itself, naked in the wind, in the air, like I'm doing it here to pass, to make a short through it, this is not good, this is not correct, and it really needs a load. That's it. Thank you very much for watching. I hope you liked my new insights about MOSFETs and my new experiments with them. And hopefully, I really hope in the near future I can actually put or find a way to drive to the maximum this MOSFET is allowed to drive and not burn it up and not having issues or problems with the switching or with those kind of switchings that I'm having there or whatever, you know. I hope I can find a solution. But for now, at least I enunciated a principle that it should work as. And that's a progress, a little step, but it's a progress. Okay, thank you very much for watching. And I say goodbye from your favorite artist electronist here, Mr. Q12, and see you later, alligator. Be nice and be cool, and also leave a like there to my movies that I'm making them with quite a hard work. All right, that's it. Bye-bye.